So if I take a look at this function, it looks very complicated. So let's go ahead and try to simplify it first. I can see here that I can factor out x squared. And then I have x squared times x minus 2 over x squared minus 1 times x minus 2. And now I can see that the x minus 2 cancels out, okay, in the top and bottom. And so we get x squared over x squared minus 1. So we were able to simplify that function, and so we're saying that y equals x squared over x squared minus 1 is the same exact function as this one, except for one minor piece, which is the fact that over here, the function is not defined when x equals 2, because it would make the denominator 0. Okay, so we're saying that these two functions are exactly the same, except for the fact that this function right here does not exist at x equals 2. So if I were to sketch out the graph of this function, it would be the same exact function as this one, except I remove one point where x equals 2, and that's why we call it removable discontinuity, right? So step 1, we find the domain of the function, and the domain, well, we can see here where this function is defined, right? So we think, what possible x values can I plug in such that I'll get some y value out of it? If I don't get a y value, if I get something that's undefined, then that means it's not in the domain. So I know that if I plug in x equals 1 or x equals negative 1, that makes the function undefined. I also know that in my original function, if I plug in x equals 2, that will make the function undefined because the denominator is 0. So my domain is all real numbers except x equals 1, negative 1, and 2. Let's try to write that in proper notation. So there's two ways that we could write this. We could write it as a set in set notation. So we have a curly bracket. Okay, and then we say x such that x is not equal to plus or minus 1 or 2. So again, what this means is we're saying the set of all x values such that x is not equal to plus or minus 1 or 2. So this vertical bar just means such that. So we could write it like this, or we could write it in parentheses notation. So I have negative infinity to negative 1, union negative 1 to 1, union 1 to 2, union 2 to infinity. This takes up more writing, so I like to write it this way when I have a lot of discontinuities, but it's up to you. But otherwise you'd have to write it like this, and the reason we write it like this is to not include negative 1, 1, and 2, right? Otherwise it's all real numbers. So when I ask you for the domain, you should write it as a set, right? So it should be in either one of these two forms. We have open parentheses here because we don't ever include infinity or negative infinity, right? It's not an actual number. We can't plug infinity into the function. So we say here that it's open parentheses. Step 2, we find the intercept. If I want to find the y-intercept, that's where it crosses the y-axis. So I look at where x equals 0, because along the y-axis, that's where x equals 0. So if I plug in x equals 0, I just get 0. Now let's go ahead and find the x-intercept. If I want to find where it crosses the x-axis, I find where y equals 0, because along the whole x-axis is where y equals 0. So I go ahead and replace y by 0, and now I know that that's true when the numerator is 0, or in other words, just x. So here, I notice that when x equals 0, y equals 0, and when y equals 0, x equals 0. So we can see here that we actually have the same intercept. They both give us the same thing, right? So they both give us the same thing, so we have just one intercept at 0, 0, which makes sense because it crosses both the x and the y-axis at 0, 0. So it's the same intercept. So what we could do here is we could just look at the simplified form of the function, right? Because everything is going to be the same about this graph in comparison to this one. The only thing that we have to do at the end is to remove the point at x equals 2 because we have a removable discontinuity. That's the only difference. So while we work through these problems, we're going to work with a simplified function, but remembering that we have this removable discontinuity. So maybe I'll write somewhere here that we have a removable discontinuity. That way, at the end when we graph it, we don't forget to actually graph it. Okay, so I'll just write it here in my domain, just so I remember that I have it on the page, that when I graph it, I'll remember to look back and I'll know to actually remove that point at x equals 2. Step 3 is symmetry. So I know that if I plug negative x into the function, so I basically replace my x by negative x, if it equals negative f of x, it's an odd function, meaning the function reflects through the origin. If f of negative x equals f of x, if it equals the original function, then it's even, meaning the function reflects through the y-axis. So let's go ahead and replace all the x's by negative x and see whether this function is odd or even. Remember, y can be replaced by f of x. It's the same thing here. So I could say f of negative x equals negative x all squared over negative x all squared minus 1. And if I square it, I know that negative now becomes a positive. So this just gives me x squared over x squared minus 1, which is exactly what the original function was after we simplify, right? So this is exactly what the original function is after we simplify. So this is just equal to f of x. So we have f of negative x equals f of x, which tells us that the function is even. So now we move on to step 4, which is the asymptote. So let's go ahead and do horizontal asymptotes first. We have a horizontal asymptote when we have a finite limit as x approaches infinity and or x approaches negative infinity. So if I think about the graph of tan inverse, for example, we know it has a horizontal asymptote at y equals pi over 2 and y equals negative pi over 2. Because as x approaches infinity, okay, the limit of the function is pi over 2, and as x approaches negative infinity, the limit of the function is negative pi over 2. So as you find the limit as x approaches infinity and negative infinity, if you get some finite limit, then that's a horizontal asymptote. If you get that the limit's infinity or negative infinity, it wouldn't be a horizontal asymptote. For example, y equals x cubed, as x approaches infinity, this function just moves towards infinity, right? It just approaches infinity, it just gets larger and larger. So there's no horizontal asymptote there. So to find the horizontal asymptotes, we have to find the limit as x approaches negative infinity and x approaches infinity. We have to do both, otherwise we might miss one of the asymptotes. Because here, if I only checked x approaches infinity, I would miss out on this asymptote. What I can do here, I can't always do this, but I could do it in this particular problem, is I could group together the positive and the negative infinity. Because I know here that all my x's here are being squared, they all have an even exponent, which tells me that if I plug in a negative value, it's just going to become positive, right? So if I plug in x, or if I plug in negative x, it's going to give me the same thing. So whether x is approaching infinity or negative infinity, it's going to give me the same result because I'm squaring it. So let's go ahead and group them together. And again, this isn't always going to work, but it'll work for this problem because my exponents are even. So there's two ways we could approach this problem. We could do L'Hopital. If you wanted to do L'Hopital, we could do that because we have infinity over infinity. So you're welcome to do L'Hopital. We would have to do it twice, so you could try that on your own. Or we could divide by the term with the highest power in the denominator. I call this method garbage rule. So it's not the official name, but it's just something to call it, right? We want to divide by the term with the highest power in the denominator to get rid of stuff, and so that's why we call it garbage rule. So I will always refer to it as garbage rule, and so what we're doing is we're finding the term in the denominator with the highest power of x, which is x squared, and dividing the top and bottom by it, and you should have seen this in chapter 2. So now we divide with the term with the highest power on the top and bottom, and we want to simplify that so that we could find the limit. So again, the point of this is to get rid of stuff, get rid of some of the x squares, because that's what's making this indeterminate form be infinity over infinity, right? That's what is making this be infinity over infinity, which we know is an indeterminate form. We cannot determine the limit as is, so we want to get rid of some of those x's here so that we don't have infinity over infinity anymore. So if I divide the top and bottom by x squared, that will help me. And now I simplify this function and I get 1 over, and then I can split this numerator, and I get 1 minus 1 over x squared. And now when I take the limit of this, I know that 1 over x squared approaches 0, so I have 1 over 1 minus 0, which is 1. So we get that the limit is 1, so that means as x approaches infinity, or x approaches negative infinity, we know that the function is approaching 1, right? The y value is approaching 1. So we don't just say horizontal asymptote is 1, we always write the asymptotes as an equation, so we say y equals 1. So my horizontal asymptote is y equals 1. We're thinking about it as equation of a line because that's where the asymptote is. That's what the function is approaching. Now we move on to vertical asymptotes. Vertical asymptote is if we approach some x value from the left or right and the limit happens to be positive or negative infinity. So here we could see the left is approaching infinity, here we could see the right side is approaching negative infinity. We don't have to have both sides approaching infinity or negative infinity, we just have to have at least one side be approaching positive or negative infinity. So to find when this is true, we have to prove using limits, and whatever we choose as a vertical asymptote, the limit as we approach from either the left or right must be positive or negative infinity. So what we want to do is we want to hypothesize that the vertical asymptote is where the denominator is 0, but we have to prove it using limits. So we have to say, okay, well, is it actually a vertical asymptote? If we approach from the left or right, does the limit approach either positive or negative infinity? Because if it doesn't, then it's not a vertical asymptote. And here is an example where we can't just assume because the denominator is 0 that it's automatically a vertical asymptote. Because here what happens is we have a removable discontinuity at x equals 2, so it's not necessarily going to be that if the denominator is 0 we have a vertical asymptote. So that's why we have to check vertical asymptotes by using limits. Okay, so I should see somewhere in your solution that if you come up with a vertical asymptote, you have to prove that it is a vertical asymptote by finding the limit as x approaches that x value from either the left or the right, and that the limit is infinity or negative infinity. So we hypothesize that the vertical asymptote is x equals plus or minus 1 because that's where the function is undefined there. That's where the denominator is 0. We ignore the fact that x equals 2, even though that also makes the denominator 0, because we already know there's a removable discontinuity there. So we already know there's no vertical asymptote there. So let's hypothesize x equals plus or minus 1, and it probably will be, but let's prove it using the definition using limits. So again, we have to approach both 1 and negative 1 from either the left or right, and to just prove that the limit's either positive or negative infinity. So even though you only have to use one direction for each positive 1 and negative 1 to prove that the limit's positive or negative infinity, I'm going to do both sides and then I'll explain why later. Let's go ahead and find the limit of these. What I want to always try first is inspection or direct sub. Okay, so I'm going to try direct sub, and when I try direct sub, I plug in 1 and I get 1 over 1 minus 1, which is 1 over 0. So I have that direct sub gives me 1 over 0, and so now what I'm going to do is something that I call plug-in rule. Again, that's not an official name, I just make it up so that I have something to refer to that limit method by. So I have 1 over 0, which tells us that the limit must be either positive or negative infinity. Because if you think of the top approaching 1 and the bottom is approaching 0, then it's 1 over a really, really, really small number, which is either approaching positive or negative infinity, depending on whether that really, really small number is positive or negative. What I want to do here is look at x being slightly larger than 1, and then x being slightly smaller than 1, and seeing what the value of the function is there. Because if the value is positive a little bit to the right of 1, then I know if it's either approaching positive or negative infinity, it has to be positive infinity if the right side of this is a positive value. And same thing with negative. If I look a little bit to the right of 1 and I get a negative value, then I know it has to be close to negative infinity. So again, I call this method plug-in rule, or I just abbreviate it as PIR, so anytime you see that now you'll know what I'm talking about. So again, we'll use plug-in rule. So now I think what happens when x is a little bit larger than 1? Don't actually plug in a value, okay, because it's very unsophisticated. We don't want to do that here. We want to actually use concepts to prove it, right? So we don't want to plug in something, so you could just think about it in your head, or maybe just do the work on the side. So if I think about this, if I plug in something slightly larger than 1, like 1.0001, but again, don't actually plug it in. So here, I know that this is if I square that, it's going to be larger than 1, so the bottom is going to be positive, and the top is always positive because it's squared, so I have a positive over a positive, so that tells me the limit's positive infinity. Here, x is approaching 1 from the left, so if I think about something slightly smaller than 1, like 0.9999, if I square that, it's still going to be less than 1, so I'm taking a number smaller than 1, and then I subtract 1, so that's going to give me a negative number on the bottom. On the top is a square, it's always positive, so a positive divided by a negative is a negative. So again, if I do direct sub and I get 1 over 0, that doesn't mean the limit's undefined, right? It doesn't mean the limit doesn't exist, because we're not actually finding the value of the function at x equals 1. We're thinking what happens as we approach 1. So here we're not thinking, what is the value 1 over 0? We're thinking, what happens when the function approaches something like 1 over 0? Which again is going to approach close to positive or negative infinity because I have 1 over a really, really, really small number, like 1 divided by 0.0001, right? That's going to be close to infinity, or I could try 1 over negative 0.0001, and that's going to be close to negative infinity. So I'm going to look slightly to the left of 1, right? I have, again, a positive, and I have a negative, so this gives me negative, and if the limit must be positive or infinity, and here I have a negative value to the left of 1, then it must be negative infinity. Now, to the left of negative 1, right, I have negative, say, 1.001, so I square that, now it becomes greater than 1, because I square it becomes positive, so this is positive over a positive, so I have positive infinity. And lastly, to the right of negative 1, like negative 0.9999, I square it, it becomes less than 1, so I have positive over negative, negative infinity. I found my limits on each side of x equals 1, and I found the limits on each side of x equals negative 1. To prove it's a vertical asymptote, again, you only need to do one of the sides for each of these, because as long as the function is approaching either positive or negative infinity on one side, then that tells us it's a vertical asymptote. However, I highly recommend that you do both sides. It doesn't take much extra work, but I recommend that you do both sides so that when you graph the function, it's much easier to be able to tell what the graph looks like, and I'll explain more on that later. But again, I prefer to do all 4, but if you don't want to do all 4, you at least have to do one side of each, right? Prove that it's a vertical asymptote, because you cannot just assume it's a vertical asymptote because the denominator is 0. Because the denominator is 0, we can hypothesize that the vertical asymptotes are x equals plus or minus 1, but we had to prove it using limits, and as long as the limit is either positive or negative infinity on either the left or right side of each of them, then we know that they are vertical asymptotes. Now we move to steps 5 and 6, which is to find increasing and decreasing and local max and min. You could try calculating the derivative on your own. I'll skip that part. Once we calculate the derivative and simplify, we could find the critical numbers. And so we set that equal to 0 and see what makes... So we could set this equal to 0, and then we could solve for x. So I know that this equals 0 when the numerator is 0, or when x equals 0. Also want to check when the derivative is undefined, because we learned that in section 4.1, if I plug in some x value, it makes the derivative undefined, but it's also in the original, it's in the domain of the original function, then it's still a critical number. So we know that this derivative would be undefined when x equals plus or minus 1, but that's not in the domain of the original function, but we still want to include it on the number line, okay? So we still want to include the number line because if I have a discontinuity there, what if on one side I'm increasing, on one side I'm decreasing? I have to include on the number line so I make sure that it doesn't change between increasing and decreasing there, because it might. So again, when x equals plus or minus 1, it makes the derivative undefined, which tells us it could potentially be a critical number, but since it's not in the domain of f, it's not a critical number, so it can't possibly be a local max or min, but we still want to include it in the number line to divide up the intervals of increasing and decreasing. We'll also want to include x equals 2 because we know we have a removable discontinuity there, so we can't include that in the intervals of increasing and decreasing. So I drew my number line, I color-coded x equals 0 because when x equals 0, that's the only possibility that we could have for a local max or min because that's where we have a critical number. All the other points on the number line cannot possibly be a local max or min because they're not defined there, but we still have to include the number line because it could switch between increasing and decreasing there. Also, when we write our intervals of increasing and decreasing, it cannot include any of these discontinuities, so another reason to put it on the number line, so we remember to not include that. Now I look at my derivative and see at each interval, whether it's positive or negative, we always want to try to find a shortcut, right? So if the denominator is being squared, then I could pretty much ignore the denominator, because if it's being squared, it's always positive, and anytime I divide something by a positive number, it's never going to affect the sign. Right? That's all we care about is a sign here. We don't care about the actual value at each interval. We only care whether it's positive or negative. So if I divide by positive, it's not going to change anything. So I could just look at the top and figure out the sign from there. Well, I know that if I plug in a positive x value, I always have a negative for the derivative. So my positive x's will always be negative. Then if I plug in a negative x, I have negative 2 times negative number, so that's positive. Since this represents my derivative, I know I have a positive slope and then I have a positive slope and I have a negative slope, so it's going to increase and then it's going to decrease, and that's going to tell me that I have a local max there. So let's write out our intervals of increasing and decreasing, and then our maximum. So my intervals of increasing occur where the derivative is positive, negative infinity and negative 1, union negative 1 to 0, right? So I always have open intervals when I talk about intervals of increasing and decreasing, because it wouldn't be increasing or decreasing over here at that critical number, and it wouldn't be increasing or decreasing at any of the discontinuities because the function doesn't exist there. So I have to keep it split. I cannot combine this into one interval, even though these intervals are adjacent, because we know that the function can't be increasing at negative 1 if the function doesn't exist there. So always open intervals for intervals of increasing and decreasing. So I have negative infinity and negative 1 is 0 as my intervals of increasing, and then my intervals of decreasing happen where the derivative is negative, again, keeping the open intervals and keeping these intervals separate because I can't have a function be decreasing where the function doesn't even exist. And then my local max was at x equals 0. If you want to find the y coordinate, we would plug it into the original function. I plug in x equals 0 into here. However, in step 2, when I found the intercept, I already know that when x equals 0, y equals 0. So if you could go back to step 2 and see if you already did it, it might save you some time. And so I already know that the y value is going to be 0, so I have a local max at 0, 0. Sometimes I'll say, just give me the x value where we have a local max or min. Sometimes I'll ask you for the point x comma y, which you would find right here. And typically for these curve sketching problems, you will want to find the whole point x comma y because you will want to label it on your graph. Now step 7, find the intervals of concavity and find if there's any inflection points. Again, check the second derivative on your own, and you'll have to do quotient rule and simplify. So here we could see that this second derivative is actually never 0, because if I look at where the numerator is 0, well, 3x squared plus 1 is always positive, so I know here that this is never 0. The only thing that I have to put on my number line is my discontinuities, right? So always include your discontinuities on the number line. Same reason as before, because the function can't be concave up or concave down if the function is discontinuous, because the function doesn't exist there. And where the function doesn't exist, it still may change between concave up and concave down. So we must include them on the number line. So looking at the sign of my second derivative, I have the top is always positive no matter what. So again, just ignoring that, because if I have a positive, then it's not going to affect the sign. So all I have to do is look at the bottom. All right, so if I look at the bottom, then I know if x is greater than 1, I'm going to have a positive value, and then if I cube it, it's still going to be positive. Same thing if x is less than negative 1, because I'm squaring it, so it's the same concept as if x is greater than 1. And if x is between negative 1 and 1, then when I square it, I'm going to have something smaller than 1, so this is going to be negative. I cube it, it's still going to be negative. So I look at where the second derivative is positive. Those are my intervals of concave up, so CU is concave up. Again, I cannot combine these two intervals right here. I can't just consolidate them, okay, because the function doesn't exist at x equals 2, so we can't possibly have it be concave up. Concave down is where the second derivative is negative, so concave down is negative 1 and 1, because that's where the second derivative is negative. So we can see here why it's important to include the discontinuities in our interval, because again, at a discontinuity, the function couldn't change between concave up and concave down, or increasing and decreasing, right? So we have to include those discontinuities in our number line. Now remember that all of these are discontinuities, so the function doesn't exist there, so be careful when you look at your inflection points. Because we can say, okay, an inflection point is where the second derivative changes sign, but there's two key pieces for an inflection point. The first thing is that the second derivative must change sign. Yes, okay. But then the second thing is that that x value must be defined in the original function, meaning it must be in the domain. And if I look at all three of these, okay, well, it looks like there could be inflection points here, but there's actually not, because these two x values are not in the domain of the original function. The function doesn't even exist there, so how could the function have an inflection point there if it doesn't even exist there? So you want to be careful when you do your inflection points and local max and min, because when you draw these, you have your discontinuities, but be careful, just because it changes sign, it doesn't mean that it's going to be an inflection point. So that's why I color-coded that green 0 before in the previous step, to remember that's the only point where we could have a local max or min, and here we don't have any points where we could have inflection points, because the only parts that we have that would change sign are not in the domain of the original function. Now step 8, time to graph. So before we graph, what I like to do is I like to combine the number line from steps 5 and 6 and from step 7, because otherwise it gets confusing trying to combine the increasing and decreasing with the concavity. So I like to just put on the number line, especially if the intervals are different. So I'm going to take all the breaking points of steps 5 and 6 and all the breaking points of step 7 and combine it onto one number line, and then think about individually where it's increasing, decreasing, and the concavity, and put it onto one number line. So if I combine all the breaking points of steps 5 and 6 and step 7, here are all my breakouts. Now I determine each of these from steps 5, 6, and 7. So from steps 5 and 6, I know that if I have x less than 0, it's going to be increasing. And when x is greater than 0, I have decreasing. So from step 7, I know that I have concave up when x is less than -1. Between -1 and 1, I have concave down, so now I write concave down twice for both of these intervals. Between 1 and 2, I had concave up, and then from 2 onwards, I have concave up. So now it's going to be much easier to draw the graph. The first thing that I like to take a look at are all the coordinate points, so all the intercepts, all the max min, and all the inflection points, because that's very easy to graph. So I know that I have an intercept at x equals 0, basically the only coordinate point I have, because the local maximum is also occurring there. Then I have the asymptotes. The asymptotes are x equals plus or minus 1, which we draw with dotted lines. Let's label those with equations. And then we also have the horizontal asymptote y equals 1. From step 4, I also found limits, right? So those limits will help me now to draw my graph. We found that as x approaches -1 from the left, the limit is positive infinity. So I'm just going to draw a dash up there because I know my graph should eventually end up there. As x approaches -1 from the right, we found that the limit was negative infinity. So let me just draw a dash there so I know the graph must end up there. As x approaches 1 from the left, we found that the limit was negative infinity. And x approaches 1 from the right, we found that the limit was positive infinity. So that just gives me a better idea of where my graph will be, which is why, again, in step 4, when I did the vertical asymptotes, I found the limit on both the left and the right side instead of just doing one side for each. I would save symmetry for last. Symmetry is kind of just like a good check to make sure that if we have symmetry, it shows up on the graph. Now we're ready to use our number line. So I know that when x is less than -1, I have increasing and concave up. Well, I know my graph should end up there, right? And I also have a horizontal asymptote, so the function must be approaching this as x goes towards negative infinity. So I know it's going to look like this. And then when x is between -1 and 0, I have concave down and increasing. So I know I'm over here by my limit from step 4, and then I'm going to go to up here. From 0 to 1, I have concave down and decreasing. So I have my 2 connecting points, right? So that's good. Between 1 and 2, I have decreasing concave up, and same with 2 to infinity, because remember, 2 is just that removable discontinuity. So let's ignore that removable discontinuity just for a second and draw a decreasing and concave up for the rest of the graph, which we can see starts here and goes towards y equals 1 because that's a horizontal asymptote. And then after that, I'm going to remove the point where x equals 2 because I know I have a removable discontinuity there. So we'll just erase a little point there and put an open hole indicating that removable discontinuity. The last thing we need to do is to label any of the points with coordinates. So any inflection points, intercepts, max, min, inflection points, and so on. So here I have 0, 0, and then here I have the removable discontinuity x equals 2. Now I just have to find the y value, which I could plug into the original function. Or rather, I wouldn't plug it into the original function, but I'd plug it into the original simplified function. Because if I plug it into the original function, again, it will be undefined. So I plug it in here to see what the function should be at x equals 2 before we remove it. If I plug x equals 2 in, I get y equals 4/3. So I have 2 comma 4/3. And that's what the graph should look like. These problems could be very lengthy, so it's important that if you make a careless mistake somewhere, okay, you know what the graph should look like because you've done so many practice problems, that you graph your graph based on your work, okay? Because if you make a mistake somewhere, I'm going to grade your graph based on your work, not what the graph should be. So any time that your graph does not match with something that you found, that's where your point deductions are going to come into play. So if you make a mistake with the derivative, or if you accidentally switch the intervals of increasing and decreasing, okay, well, don't draw the correct graph if you know what the correct graph looks like. Draw your graph based on your work, because again, that's how I'm going to grade your graph.